everybody. Now let us start this week with discussion on different topics. That is, particularly we are going to focus on a very important topic of industrial level relevance, also related to the field of crystal engineering, which we call as polymorphism. So we are going to look at different aspects of polymorphism. What is polymorphism? Why does polymorphism happen? How do we control polymorphism? What are the regulatory aspects of polymorphism? Because polymorphism is a very important phenomena in the drug industry, in the agrochemical industry, and in different fields of material science and engineering as well. And we are then going to take up some specific case studies of polymorphism, and then we are going to look at the next aspect, that is co-crystallization. Why co-crystallization is important, what is the purpose of doing co-crystallization experiments in the industry, and some other relevant applications. So to start with, let us go to the definition. So today we are going to discuss polymorphism and co-crystallization over the next few lectures. So polymorphism, it's a phenomenon in which a given chemical substance, so you can have any compound in nature. You can have an organic compound, you can have an organometallic compound, you can have an inorganic complex, you can have a peptide, an amino acid, a protein. Given a compound, any particular chemical substance that exists in at least two distinct or different internal arrangements in the crystal is referred to as polymorphism. So this is a very, very important phenomena. This is an observation which happens in nature, in which a given crystalline substance that exists in at least two distinct or different internal arrangements in the crystal. So you have a chemical substance, and when this particular chemical substance crystallizes in a given crystal structure, it is characterized by at least two distinct or different internal arrangements of that substance inside the crystal. And the word polymorphism comes from the Greek word. This comes from the Greek word which is called poly, which means many, and morph refers to the form. So we also refer to polymorphism as the existence of different forms of a chemical substance. So it also refers to the existence of different crystalline forms of a substance. And there are different nomenclatures. We can say form alpha, beta, gamma, or we can say form 1, 2, 3, and so on and so forth. So these are the different crystalline forms of a given substance, and this is referred to as polymorphism. And morph essentially refers to the form, and it also is characterized by the shape or habit of the crystal. So the first indication that you possibly have polymorphism is you take any particular substance and crystallize it under different conditions, and then you will see the existence of different morphologies. So the existence of different types of crystals of different morphologies, that is of different shapes and habits, is a possible indication of polymorphism. So the existence of different morphologies, that is different crystal shapes / habits, is indicative of polymorphism. So this is the first signature that you possibly have polymorphism, and then the idea is to take these different morphologies. For example, we can have a compound which crystallizes as needles. It can also crystallize as prisms. It can also crystallize as blocks. Okay, and then it can also crystallize as thick plates, and depending on the thickness, the plates can also be thin as well. And sometimes we can have an irregular shape as well. So these refer to the different morphologies, that is different crystal shapes and habits, and these are indicative of polymorphism. And the next way to check for polymorphism is to look at the technique of single crystal X-ray diffraction, where you determine the unit cell, and determination of the unit cell tells you whether you have polymorphism or not. So if you get different lattice parameters, this is a very strong indication of polymorphism. It is also possible that you can have different morphologies, but when you do the unit cell check, you do not get no change in lattice parameters takes place, no change in lattice parameters takes place. So because there is no change in lattice parameters, it is not indicative of polymorphism, because the internal structure, it refers to the fact that the internal structure is possibly, I am using the word possibly here, the chances are very, very high that possibly the internal arrangement of these crystals are similar. But there are very rare cases also where you can have the same unit cell, but the molecules would have possibly arranged in different ways inside the crystal structure. But for that, you will have to collect the full diffraction data, determine the structure, and then only conclude whether polymorphism is there or not. And the reverse is also possible. You can have different unit cells even when the morphology is similar. Now, how to overcome this problem? So the idea is that once you have done crystallization and you have got the crystallization container in which you have got different kinds of crystals which look similar in terms of shape, size and morphology, the idea is to randomly pick good quality, at least 7 to 8 crystals, and check the unit cells. Chances are that 1 or 2 of these will correspond to a different unit cell, and then it's an indication that the compound which you have crystallized has got 2 polymorphs. Now this is a random sampling, and this is a statistical process where you at least screen a minimum number of crystals so that you get a possible indication of polymorphism by the existence of different unit cells. So it all depends upon the kind of efforts you are willing to put into investigating your batch of crystals. In most of the cases, the chemists are more interested to know the molecular structure only. They are not really interested about the solid state diversity or other aspects of polymorphism of that particular compound. But interestingly, it is the solid state diversity which renders polymorphism very interesting, and the properties which you get from this phenomena are also expected to be different, and therefore this is a very, very interesting area of investigation and further research. So now both things are possible. You can have same unit cell for different morphologies, and you can have different unit cell for same morphology, and that will allow you to establish whether you have polymorphism or not. Now, what are some very important features about polymorphs? So to start with, we said that they have different crystal structures. In which, because they have got different crystal structures, the arrangement of atoms, ions or molecules are different. And the implications of this is that the physical properties and in some cases the chemical properties of the polymers are different. So to start with, we can say, for example, the density of the solid, the melting point, density, melting point, solubility, etc., lattice energy. These are some of the properties which are going to be different for different polymers: the density, the melting point, the solubility, and the lattice energy. So these are some of the most important characteristics of polymorphs. It is a solid state phenomena. Definitely the occurrence of polymorphism and the relevance of polymorphism is only in the solid state, because once the compound has dissolved in a particular solvent, either in aqueous medium or in other polar solvents or non-polar solvents, then the molecules by and large exist in the solvated state, where it exists as a monomer and can exhibit its characteristic chemical reactivity. But some of the most important properties are, as I mentioned to you, density, melting point, solubility, and lattice energy. These are going to be very different. This also has implications in terms of applications. So this has implications in the applications of polymorphism in the drug industry, in the dyes and pigments industry, in agrochemicals, in electronic materials, for example, we have got optoelectronic materials, and they also affect the thermal and electrical conductivity of materials, and and then you can also have energetic materials which find applications in the field of design and synthesis of rocket propellants, fuels, and so on and so forth. So there are a large number of industries which are affected by this phenomenon of polymorphism, and therefore this has got very important significance in the pharmaceutical industry. And as I mentioned, all kinds of substances, whether they are organic or inorganic origin, do exhibit polymorphism, and the literature is now populated with large number of studies with large number of molecules now exhibiting this phenomenon of polymorphism. Now, when was polymorphism discovered? It was first discovered by discovery of polymorphism. So it was first discovered by Eilhart, Eilhart, Michaelis. So you know, we have all heard of the Michaelis law of isomorphism. So it was Eilhart Michaelis in 1820 who identified the different crystal structures of calcium carbonate corresponding to the calcite and aragonite phase. And he also looked at phosphates as well. He looked at arsenates as well. So he proposed different crystal structures, different polymorphic phases for these kind of inorganic substances. Then it was in 1832 that F. Waller and J. Liebig discovered polymorphism in benzamide, and then in 1938 J. M. Robertson and A. Ubelhod discovered diamods in resorcinol, that is 1,3-dihydroxy benzene. So these are some of the very initial and the early discoveries in the field of polymorphism. Some of the most relevant ones started with Michaelis, then benzamide. Benzamide is a very simple substance, but polymorphism has been discovered way back in 1832, and in the recent past few decades also people have again looked at benzamides, and then in 1938 Robertson and Bullard discovered polymorphism in case of resorcinol. And today there are some other common substances. For example, there is acetyl coumarin, I can say, which exists as polymorphs. There is a thiophene derivative which exhibits color polymorphism, and it is known to have, it's a carbonitrile derivative, it has a cyano group, it has a methyl group, and one of the NH is replaced by a nitrophenyl group. So the thiophene derivative exhibits color polymorphism, and there are nice different colors you get of these crystals along with different morphology, and this is one of the compounds which has been characterized for the largest number of polymorphs in the database. So the database we have is called the Cambridge Structure Database, where we have a large number of crystal structures reported till date, and there also for this particular thiophene derivative the largest number of polymorphs have been reported. So now the next thing we would like to learn about polymorphism. So this is the initial background to polymorphism. Now let us go and explore something more at the molecular level as regards the phenomena of polymorphism. So phenomena of polymorphism is broadly classified into three categories. Types of polymorphism. Number one, we have got conformational polymorphism. Number two, we have got packing of polymorphism. Number three, we have got pseudo polymorphism. And in polymorphism also there are two additional phenomena which have been observed. We refer these as A, concomitant polymorphism, and disappearing polymorphism, disappearing polymorphs. So these are two very interesting phenomena which also exist. We'll come to each of these one by one. So to start with, first let us look at the other observations with respect to polymorphism. So what happens is that during the process of crystallization of a compound, we will explore the aspects of crystallization in more detail in the lectures following this week later on. But as of now, when you are trying to crystallize a compound under a particular set of crystallization conditions, for example in the combination of solvents using different techniques and at different temperatures, for example you can do it at room temperature or you can do a low temperature crystallization, this space which you are giving to the compound to sample and explore before it crystallizes is referred to as the domain of crystallization. And it can so happen that this domain for crystallization, which we also call as the occurrence domain, can overlap for two different sets of polymorphs. So polymorphs, another important property is that the lattice energy is different, and the differences in lattice energy is very small, between 1 to 3 to 4 kcal per mole. So the differences are not small. So you can still have, in principle, theoretically, infinite number of arrangements are possible for a given compound. So you can crystallize a compound where you can actually sample infinite possibilities exist, an infinite number of arrangements, but what you realize experimentally is only few of these arrangements which correspond to the Gibbs free energy minima. These correspond primarily to the thermodynamic minima. You can also get the kinetic minima, where you can get kinetic crystallization conditions satisfied, and you can get kinetic polymorphs. So basically what is happening is that there is an overlap of this crystallization domain, and in which two different polymorphs with two different arrangements but having almost near similar lattice energies can crystallize out simultaneously, and that phenomena is referred to as concomitant polymorphism. So in case of concomitant polymorphism, the polymorphs are obtained under identical conditions of crystallization. Under identical conditions of crystallization in the same crystallization container. So the same crystallization container will have both these particular polymorphs, and as I mentioned to you, there is an overlap between the occurrence domain, that is the space and which is given for the compound to crystallize under a given set of conditions is referred to as the crystallization domain, and when these domains overlap, then the chances of existence of concomitant polymorphism takes place. So you can have, for example, you can take a beaker and you say you have put in a particular solvent or a mixture of solvents, and you have taken the compound of interest to crystallize. You can say that you can have needles along the faces. So you can have needles sticking to the side walls of the beaker, and the base, the bottom, which is the circular area, can have plates, because you see that the solvent is slowly evaporating and the compound of interest is crystallizing out. So you have different points of contact of the crystallizing molecule with the surfaces. That is, you can have the base surface and you can also have the side surfaces, and this is very common that you might get needles on the side walls, and you will get these plates. Sometimes you can get both plates as well as needles on the circular face also. Both plates and needles are obtained. So the first morphological indication of polymorphism is that you have got these two distinct morphologies. You have got the plates, you have got the needles, and therefore this is indicative of polymorphism. And now the idea is to take out these crystals from the crystallizing medium, or almost allow for the solvent to evaporate, and then take out these crystals and mount them, check the unit cell, and verify whether possibly they exist as polymorphs or not. So, and this the ratio in which you get the ratio of obtaining two polymorphs will vary, and that depends upon the crystallization conditions, the amount of the solute to start with, the amount of the compound you have taken to crystallize, and the size of the container or the volume of the container you have considered, and then the shape of the container. For example, you can do it in these 5 ml beakers, but you can also do it in glass vials. You can do it in small conical flasks. You can do it in NMR tubes, and there are different apparatus, different glassware which is available to be able to crystallize these compounds, and these give you the necessary platform, the surface of the container, and how much you have exposed it to the environment, what is the rate of evaporation of the solvent, and so on and so forth, to decide the possible existence of concomitant polymorphs. And during the process of crystallization, we actually close the top with a parafilm, and we make holes on this, we make perforations on these, so that the solvent evaporates off very, very slowly, and good size crystals of nice quality can be obtained for doing the diffraction experiments. So this field of crystallization is itself an independent research area, but when you do these crystallization experiments, the possibility of getting concomitant polymorphs does exist, and this observation of seeing different kinds of morphology, and also sometimes you will see that you have different morphology and you also have different colors. So you will see one is orange, one is light yellow, one is deep red, one is light orange. You can also get different kind of colors along with the different morphologies. Sometimes you can get similar morphologies but different colors. So that is also indicative of color polymorphism and the possibility of having concomitant polymorphs in the same crystallization container. Then comes the phenomena, a very important phenomena of disappearing polymorphs, where say you have crystallized a particular compound, you got one particular polymorph. Now the next time whenever you try to crystallize that particular compound, the initially obtained polymorph does not crystallize. You always get a new polymorph, and no matter whatever you do, you change the conditions of crystallization, you do screen it very extensively using different methods. Say you take polar solvents or take polar non-polar solvent combinations, or you take non-polar solvents, you change the temperature, you change the crystallization containers. Sometimes you even change the laboratory where you are trying to crystallize that particular compound, so that you do not have any possible contamination in the air which can interfere possibly with the formation of the initially obtained form. So this is a very important exercise also in the pharmaceutical industry, that people would always like to reproduce the initially obtained form. So the initially obtained form, which is no more crystallizing, is possibly the kinetic form, which would have formed at a faster rate, which would have been initially formed at a faster rate, but is very now difficult, but it is now very difficult to control, and therefore what you are now obtaining when you are crystallizing it regularly is the thermodynamic form. So you are not able to reproduce the kinetic form. Whenever you are trying to crystallize, you are only getting the thermodynamic form. So the ability to be able to isolate and characterize the kinetic form becomes extremely difficult, and this has got very severe implications in the pharmaceutical industry, and these are some of the things we will also explore later, because the kinetic form is the one which is having the higher Gibbs free energy, therefore it is more easily available in terms of the bioavailability, it can have a higher dissolution, and therefore the overall pharmacological property of that particular polymorph can be compromised if you do not have the kinetic form, but you have the thermodynamic form, because the latter is much more stable and might have a reduced solubility compared to the kinetic form. So it is very important to be able to get the desired kinetic form, but if you do not get it, then that particular form becomes the disappearing polymorph. So, and what the scientists essentially say, that some of this group of scientists believe that is nothing called disappearing polymorph. It is just that the exact conditions of crystallization, when I say exact, means it means you have everything to worry about. Even the room in which you are trying to crystallize that particular form is important. Most of the times when we do crystallization, we will have dust particles, we will have a slightly dirty room in which we are doing the crystallizations, and now if you go to a new lab where the dust is less and you don't have suspended particulate matter, then maybe crystallization might become difficult, and what you might get is a completely different polymorph compared to what you would have got in an otherwise unclean or a relatively old lab. So because you are not able to exactly reproduce the conditions of crystallization, getting the disappearing form again becomes very difficult. And there have been some case studies where trying to get it has been very important. As I told you, this has implications in the pharmaceutical industry. Now let us go to the types of polymorphism now. So we looked at first conformational polymorphism. Now in case of conformational polymorphism, we have a given molecule which has been crystallized, and it is observed, and after determination of the crystal structure. So we will come to the different techniques of crystallization of polymorphs after some time, but once you have determined the structure of the two polymorphs, you will now see the conformation of the molecule, and differences in the molecular conformation in the solid state lead to conformational polymorphism. I will write it as CP. So differences in the molecular conformation in the solid state can give rise to this particular conformational polymorphism. So you have a molecule which has been dissolved in a solution, and there are different degrees of freedom associated with the different rotatable bonds in the molecule, and when you are crystallizing out this particular molecule, it is just one of those conformations which has been crystallized out, but the other conformations also exist. So if you now change the conditions of crystallization, the chances are that you will be able to crystallize the same molecule with a different conformation, and the relationship between these two structures is that they exhibit conformational polymorphism. And what is happening is that it is essentially it is essentially the challenge here involved is that there is a competition, a very subtle competition between the non-bonded interactions which try to lock a given conformation versus the intermolecular interactions between the molecules which try to change the conformation of the molecule. So these events take place parallelly, and it is the competition between this event, that is the ability to lock the molecule in a given conformation and freeze it out, or to make it flexible and to allow for different intermolecular interactions to exist between the different molecules, thereby adapting a different conformation. And it is these two factors, the subtle balance between these two factors, which lead to the discovery of conformational polymorphism. So essentially we have got rotatable bonds which are present that essentially give rise to this phenomena. Now, for example, as I was telling you, the thiophene derivative, let us look at the structure of the thiophene derivative. You have this cyno-substituted, the carbonitrile and methyl, and then here you have the NH. So here you have got the nitro compound. So this is the thiophene derivative, and this exhibits flexibility in torsion around this particular bond. Keep in mind that this particular NH is involved in a NHO intramolecular hydrogen bond. So this particular conformation is locked, but it is a flexibility about the CN bond that leads to conformational polymorphism, and this is also exists in different colors like red, orange, yellow, light red, deep orange, deep yellow, and that is why this is also referred to as ROY. Its code name is actually ROY because of it exhibits color polymorphism. Another very interesting compound which exhibits a conformational polymorphism, I am drawing the structure here, is this particular compound which is again has got rotatable bonds here, and therefore has the ability to exhibit conformational polymorphism. In the second case, we have got packing polymorphism, where you will essentially have a molecule which has got the same conformation in different crystalline arrangements, but the arrangement of the molecules via the presence of different intermolecular interactions, which comes from the concept of synthons, as we discussed in crystal engineering. So it is the arrangement of the primary synthon blocks or the primary synthon units in different ways in the crystal structure that gives rise to the phenomena of packing polymorphism. And in the third case, we have got pseudo polymorphism, where the crystal structure includes solvents, for example water, chloroform, acetone, methanol, ethanol, isopropanol, and so on and so forth. So you have a compound which is crystallized without the solvent, that's the anhydrous form, and you also have the compound which is crystallized with the solvent, which is held by strong hydrogen bonding. So this is also referred to as the solvatomorph of the parent drug. It is not strictly polymorphism because you have another chemical entity, the solvent, which is included in the crystal structure, and therefore this is referred to as pseudopolymorphism. However, pseudopolymorphism, particularly the hydrates, are extremely important in the pharmaceutical industry because they exhibit enhanced properties, for example enhanced solubility because of the presence of water in them. So that is why these pseudopolymorphs, particularly the hydrates, are very relevant because of these enhanced properties, the bioavailability, and they have very important relevance in the pharmaceutical industry. So with this we have looked at the types of polymorphs, and in the next lecture we will now continue further into the field of polymorphism. Thank you.